return, the Pythagorean theorem. Because we're talking about the Pythagorean theorem today and its converse, which might be new for some of you, I felt that it was a good time to introduce Edpuzzle, which is a great app that I'm going to use to help monitor your progress in watching a video and taking notes. Something that I will enable in the Edpuzzle is the ability to complete the guided questions. So your video will pause and require that you answer the questions correctly in order to move on to the remaining parts of the video. Full completion of your Edpuzzle will be required for a grade, just to ensure that everybody is doing their best to understand the material. So if you have two sides of a right triangle, you can always find the third side using, drumroll please, the Pythagorean theorem. So if a triangle is a right triangle, which we know is a key idea, must have this satisfied, then the sum of the squares of the lengths of the legs is equal to the square of the length of the hypotenuse. Okay? We have been using the Pythagorean theorem to help us find side lengths of figures in the coordinate plane. Okay? The big idea to remember that it's leg squared plus leg squared equal to the hypotenuse squared. So notice I have triangle ABC here. Across from angle A is little a. Across from big B is little b. Across from big C is little c. Capital letters represent angles, lowercase letters represent their appropriate side lengths. So we have a squared plus b squared equals c squared, because c is across from the right angle and c represents our hypotenuse. Okay? There are a few special numbers that occur. So my key thought is a Pythagorean, let's see if I can spell that, triple is a set of non-zero whole numbers. Okay, so whole numbers, meaning can't be a fraction, can't be a radical, A, B, and C that satisfy the equation of a squared plus b squared equals c squared. AKA the numbers satisfy the Pythagorean theorem. For example, 3, 4, 5 has come up a lot in our notes. 5, 12, and 13 would be another great example. And then 8, 15, and 17 would be another great example. Throughout our notes today, we will figure out more Pythagorean tables that you might want to add to this section of your notes. Might be a good idea to start keeping track of a list of all of the Pythagorean triples that exist. It'll make your life a lot easier. First example, it says, what is the length of the hypotenuse of triangle ABC? Do the side lengths of ABC form a Pythagorean triple? Explain. I am noticing in this problem here, I am given side length B, because it across from angle B. I'm also given the side length for A. C represents my hypotenuse because C is across from the right angle. Therefore, we have leg squared plus leg squared equals my hypotenuse squared. C will not always be your hypotenuse. It always depends upon the setup of your triangle. So we got 21 squared plus 20 squared equals C squared. Alright, so I need to simplify my left-hand side. 21 squared plus 20 squared. We have 441 plus 400. Can't do anything yet with C squared. 441 plus 400 is 841 equals C squared. And then, to get C completely by itself, I'm just going to take the square root of both sides. And the square root of 841 is 29. Okay? Now, I want you to remember in Algebra 1 that whenever you take the square root of a quantity, you're supposed to have a plus or a minus. But we don't need to worry about the plus or the minus, because in the context of this problem, we're finding the side length, we must find positive values. Therefore, the length of my hypotenuse is 29. The question next said, do the side lengths of ABC form a Pythagorean triple? Well, the answer to that question is yes. My values for A, B, and C all represent whole numbers, okay? And they are satisfying my Pythagorean theorem, okay? So whole numbers, they satisfy A squared plus B squared equals C squared, okay? Here's your very first got it. Got it, question 1A. The legs of a right triangle have lengths 10 and 24. What is the length of the hypotenuse? Do the side lengths in part A form a Pythagorean triple? Explain. Here is your first question to answer yourself. All right, checking your answer from 1A and 1B. You should have that the side length for 1A is 26, and therefore, because the hypotenuse is 26 and my legs are 10 and 24, they are all whole numbers, therefore they are Pythagorean triples. Example number 2, we are finding the length of a leg. In this situation, I am noticing that 20 represents the length of my hypotenuse because he is across from the right angle. Therefore, my missing piece is one of my legs. Okay? So we're going to have x squared plus, well, the other leg that appears in my life is 8. So we're going to have 8 squared. We're going to set this equal to our hypotenuse squared, so 20 squared. All right, so we're going to start to solve for our variable here. So we have x squared plus 8 squared is 64. 20 squared is 400. Next thing I'm going to do is I'm going to subtract 64. So we have x squared equals 400 minus 64 gets me 336. Okay? All right, so now I'm going to take the square root. Unfortunately, 336 is not a perfect square. So I'm thinking to myself, all right, what are two numbers that multiply together to be 336? So I have the square root of 16 times the square root of 21. Notice I chose the square root of 16 because that was the biggest perfect square that appeared in 336. And 21 cannot be reduced any further because 21 is really 7 times 3, and neither are perfect squares. Therefore, my final answer is x equals square root of 16 is 4 times the square root of 21. Notice my final answer here is in simplified radical notation. Because this answer is not a whole number, these values do not represent a Pythagorean triple. Here is your next guided question. The hypotenuse of a right triangle has a length of 12. One leg has a length of 6. What is the length of the other leg? Express your answer in simplest radical form. This is the next question for you to complete yourself. Checking your answer for question number 2. You should have gotten an answer of 6 root 3. 6 times the square root of 3. All right, let's get real here with the Pythagorean theorem. So dog agility courses often contain a seesaw object, as shown below. To the nearest inch, how far above the ground are the dog's paws when the seesaw is parallel to the ground, okay? Thinking about what that actually means. When the seesaw is parallel to the ground, I have to sneeze. Woo, I have to sneeze. Okay, by saying that, I don't have to sneeze anymore. Anyway, all right, so paws. That means we're going to have a paw here, a paw right here, paw right here. So that means they're all going to be the same height away from the ground. So the focus of my life right here will be on this leg of the triangle. And I know that it's a leg because I'm observing my right angle exists between the height and the ground. And across from my right angle is a hypotenuse length of 36. So I know when I'm setting up my Pythagorean theorem, I'm going to be equal to 36 squared. I do not know my height, so I'm going to use h as my variable. Plus, we have this measure of 26 inches, and that represents a measure of my leg. I'm now going to start to solve for h. 26 squared is 676. 36 squared is 1,296. We're going to subtract 676 from both sides, and we get 620. Because this is a real-world problem, I do not need to have us leave this in radical notation. I'm going to take the square root. I take the square root of 620, and this tells me that my answer for my height is 24.899. For our purposes, I'm going to let us round, so this means 25 inches. The paws of the dog are 25 inches above the ground. Okay? Here is your question. Your question deals with a computer monitor. The size of the computer monitor is the length of its diagonal. The same actually goes for TV screens in case you were curious. You want to buy a 19-inch monitor that has a height of 11 inches. What is the width of the monitor? Round your answer to the nearest 10th inch. I'll give you a hint here. Might be a good idea to draw your right triangle and appropriate label. Okay? If you want to know the inch or the length of a You want to have a 19-inch monitor. That means that 19 inches is correlating to my diagonal, aka 19 inches is going to refer to my hypotenuse. The height is 11 inches. So here is the setup. You need to solve for your width. All right, let's check your answer on this question. Hopefully you got an answer of 15.5 inches for your width. Almost done, getting there. Converse of the Pythagorean theorem. Many of you actually already used this before in your test, whether you knew it or not. It says, if the sum of the squares of the lengths of two sides of a triangle is equal to the square of the length of the third side, then the triangle is a right triangle. What this actually means, basically, if the Pythagorean theorem works, if our equation holds true, then we know the triangle is a right triangle. If the equation does not work, if it does not hold true, then the triangle is not right. So here's my problem. A triangle has side lengths of 85, 84, and 13. Is the triangle a right triangle? Explain. So what I'm questioning is whether or not a squared plus b squared, whether or not it indeed equals c squared. So that's my proper notation. So I need to figure out which side length goes for which variable. Please remember, the hypotenuse of a right triangle will always be the largest side of the triangle. Okay? Therefore, my hypotenuse will be 85. Now, it does not matter which leg I use for A or B. So I'm going to do 84 squared plus 13 squared. And please remember, I'm still questioning whether or not this is true. So I'm still using this proper notation of questioning its equality. All right, so I start to solve. 84 squared is 7,056. 13 squared is 169. Questioning whether or not this is equal to 85 squared, which is 7,225. Combine like terms on my right-hand side, and this gets me 7,225. And so I ask myself, does 7,225 equal 7,225? Indeed it does. Therefore, the Pythagorean theorem holds. Therefore, yes, we have a right triangle. Okay, because the Pythagorean theorem works. Now here's a question. These numbers, they're all whole numbers. Therefore, 85, 84, and 13 are a Pythagorean triple. Just another observation of what you can add onto your list. I believe you could also have added questions from number 1. Here's your got it. Your got it deals with a triangle that has side lengths of 16, 48, and 50. Is it a right triangle? Explain. Question B says, once you know which length represents the hypotenuse, does it matter which length you substitute in for A and which length you substitute in for B? Explain. I kind of already alluded to that, but let's see what you think. All right, checking your answers. Answers for question 4. In the first question, you should have figured out that the Pythagorean theorem is not satisfied. Therefore, we do not have a right triangle. You should have ended up with a statement that the 2,560 equals 2,500. It's like, huh? I've never heard of that. Therefore, it's not true. In question 4b, just like I talked about, no, it does not matter which order we plug in values for A and B. Rounding out the first section of Chapter 8, we deal with the fact that not all triangles will be right. So here's our test to figure out what kind of triangle we have. So if the square of the length of the longest side of a triangle is greater than the sum of the squares of the lengths of the other two sides, then we have an obtuse triangle. Okay? So I'm testing whether or not if this statement holds true. Is c squared greater than a squared plus b squared? If this is true, then we have an obtuse triangle. And if we go in reverse, if the square of the length of the longest side of a triangle, if it is less than the sum of the squares of the other two sides, then we have an acute triangle. So if c squared is less than a squared plus b squared, then we have an acute triangle. Okay? You'll deal with these triangles actually a little bit more when you get into Algebra 2 and Pre-Calculus. Let's take care of our last example. So a triangle has side lengths of 6, 11, and 14. Is it acute, obtuse, or is it right? So the setup that I'm going to use for this one, instead of having a questioning equalities, I'm going to use a blank box. Okay? both of those theorems, all of the theorems we've dealt with today, featured an a squared plus a b squared, and somehow it was related to c squared. So once again, I need to figure out what I'm plugging in for where. C represents the largest side. Therefore, we're going to have 14 squared. Somehow, it's going to be related to the other side of my question, where we have 6 squared plus 11 squared. Now I'm going to start to simplify. 14 squared is 196. I still don't know my relationship here. 6 squared is 36. 11 squared is 121. I'm going to simplify, so we have 196 with some sort of relationship. 36 plus 121, we get 157. Alright, so therefore, 196 is greater than 157. So I can now plug this back in, so we have c squared is greater than a squared plus b squared. Because this statement is true, therefore my triangle that I have is obtuse, based upon the theorem that we just talked about. Because the length of the longest side is greater than the sum of the lengths of the other two sides. Last question for you to try on your own. I give you a triangle that has side lengths of 7, 8, and 9. Is it acute, obtuse, or right? Try it yourself and you're almost done. Checking your answer. Hopefully you got the answer. We have an acute triangle. Congratulations, you've just survived your very first section of Chapter 8. I hope you have a really great day.